Okay guys, in this video lesson we're going to start talking about this idea of taking objects now and putting them into orbit, and how do we get them so that they can leave our orbit and never come back. Okay, to do that we need to go back to Newton again and what Newton told us about the cannon. Okay, so according to Newton, he did a lot of kind of thought experiments and things like, well, what if this happened, or what if that happened, or how about this? And then he put some math to it. Okay, so one of the things he talked a lot about was if you had a cannon and it was sitting at the top of a tall mountain and you shot it. Okay, we know that things fly in a parabolic motion with projectiles, right? We've done projectiles, so we know that. We know they're going to fall and they're going to maintain an x velocity. They're going to hit the ground some distance away from the cannon. Okay, now what he went into saying is, okay, let's take this thing and let's shoot this cannon. It's going to fall a little ways away. Now if we increase the speed and we keep shooting, it's going to keep falling further and further away from our planet. Okay? But at some point, if we shoot it fast enough, it misses the planet. Okay? It's still falling, right? It still has this parabolic motion that's happening to it, and it's still falling. It keeps falling because of gravity pulling it down. But as it falls, it just misses the planet. Okay? Now, in reality, you're not going to have a cannon on top of a mountain doing this. But the idea brings us to this idea of what is orbit. Okay? A lot of students think of orbit or think of weightlessness, this idea that is something unique or special. You leave our atmosphere and somehow magically gravity disappears and you become weightless. Okay? That's not what's happening. For something to be in orbit, or when we are orbiting around our planet, we feel weightless, okay? Not because we have no weight to us anymore. It's not because gravity disappears, but we feel weightless because when we are in orbit around a planet, we're falling. Okay, we're constantly falling. In fact, we're falling the same way you would if you jumped out of a tree and fell to the ground. Okay, the difference is we're inside of something. We're in outer space. There's no air resistance. Okay, so that fall continues to happen forever and ever and ever. And because we're falling and we're moving fast enough to our left or right or horizontally, we just keep missing the planet. Okay, that continued fall, that continued free fall, is called orbit. Okay. Now, it's considered weightless for us because the thing that's falling can't support its own weight, okay? So there's nothing there. There's no, like, floor or table or rotors or engine that pushes back up on that. So there's no weight to the person. So it's considered weightlessness, okay? That's what we deal with when we talk about being weightless, right? Okay, so now we're weightless, right? So really, all weightlessness is a constant fall. And the reason why we don't hit the ground is because of that horizontal velocity that we have, or that speed. Okay, so being that the case, we should be able to calculate how fast do we have to move so that we don't hit our planet if we are in orbit. Okay, that speed is called our orbital velocity. All right, so if we combine our gravitational equation with a previous equation, centripetal force, and we say that these forces are the same, right? Because the gravity pulls us inwards. Centripetal force is force that pulls us inwards. Set these two equations equal to each other. One thing we're going to notice is that the mass of the object that is doing the orbiting cancels out again in our math. So all it depends on is the mass of the planet you're orbiting and the radius you are from that planet. Okay. Solving for velocity, because it's squared here, we do a square root. And we say that the orbital velocity is big G times the mass of the planet being orbited divided by the radius. Okay, so notice again, what doesn't matter? The mass of the satellite. Which means you could have a speck of sand orbiting and it would have to have the same speed as an entire Mack truck or entire school bus out there, or our moon, to be giving an example. Okay, so really, the only thing that matters here is how big or how massive our planet is and how far away do you want to put it from that planet, okay? Now, if we did some kind of a quick little If we did a little calculation here, we want to say how fast does an object need to go to maintain orbit at the Earth's surface. Now, I know that's not realistic, right? Because at the Earth's surface, we have air resistance, we have hills, we have mountains, we have buildings, trees, little doggies running around. So we can't orbit at our surface. But let's just say we could, okay? If that's the case, how fast would it have to move, okay? There's a reason why I'm doing it at the surface. You'll find out shortly. All right, so things that we know. We know G. We know the mass of the Earth from previous stuff we've talked about, 5.97 times 10 to the 24th kilograms. We know the radius of the Earth, again, from previous things that we've done in the class. So it's 6.37 times 10 to the 6 meters, okay? These are all things that we would either give to you or you'd have, all right? Plugging that back into our equation, we have big G, mass of the Earth, radius, plug those numbers in, take the square root, and we get a velocity of 7,910 meters per second, okay? So that means if we're on the surface of our planet and you didn't have nothing else in the way and no air resistance, and you moved horizontally at 7,910 meters per second, you would be in orbit, or you could basically continually revolve around our planet in free fall, essentially, that we're talking about. All right? Now that's orbital motion, okay? So what do we need to do then to break free of gravitational pull? Okay, so the force of gravity is pulling us down. And how fast would we have to move to not just go to orbit, but to actually become free of that and escape the gravitational pull forever? Well, if that's the case, and we're trying to figure that out, we need to know how fast to go so our kinetic energy or our momentum or our inertia that we have is stronger than the pull that gravity has pulling us back. Okay, and we know that that diminishes the further we get away. So really, it's all about how much strength we need to get away at the surface of our planet, thus the term here, okay? So we know our orbital velocity, so how do we find our escape velocity? Now, escape velocity is that speed where you're going to basically continually progress away from the planet and never be pulled back, okay? You have enough energy, enough speed, enough momentum, enough inertia to not ever come back. You can outpower basically the force of gravity pulling on you from our planet. If you look at our equation, okay, there's not a whole lot different about this. The only difference is the 2 factor here, okay? Now be careful with this because a lot of times students will look at this and say, oh, it's just double, right? I go back here and I take my orbital velocity and I just double it. So if it was 7,910, I double that and it'd be like 15,820 or something like that would be my orbital velocity. That's not true, okay? Look closer at our equation. The escape velocity is the square root of that times 2. So it's not double the orbital velocity, it's times the square root of 2 the orbital velocity, okay? So if you want to do a quick conversion, you can, but you have to do the square root of 2, not just 2 for this, okay? So knowing that, let's figure out how fast an object needs to go to escape our planet, all right? So again, we have the same information we knew before. We know the mass of the Earth, we know the radius of the Earth, we know G. We can plug it back into the exact same equation we did before, where we have G times mass of the Earth over the radius. Now we just double that, and then we take the square root of it. If we do that, we get 11,200 meters per second. So that would be how fast we have to move to escape our orbital pull, or our gravitational pull. Now let's look at it through this perspective. The escape velocity is equal to the orbital velocity times the square root of 2, right? Because the only difference between them is the square root of 2. So we take our number from before, the unrounded version of that, okay? Multiply it by the square root of 2, and we get 11,200 meters per second. Notice how those numbers are identical, because it's the same equation, just off by a factor of square root of 2. You can use either version, okay? If you know the orbital velocity, you can always plug it in here to find escape velocity. If you know the escape velocity, you can rearrange it to find the orbital velocity. Or you can always go back to these equations and they'll do the exact same thing for you. You'll be able to solve it this way also, okay? Now, what about black holes? How do black holes work and how does that pertain to this idea, right? If you look at a black hole is actually a collapsed star, okay? So it's gotten old, it's burned up its fuel, and it goes supernova, and it collapses in on itself. Now, the result of that collapse is you create an extremely dense, extremely small piece of matter that has such a strong attraction that nothing can escape it. Okay, so the gravity of that thing is incredibly strong. All right, as a result, nothing can escape, not even light. All right, that's why the term black hole, because in outer space it looks like this black void across the heavens, which normally if we look across there, you see the speckling of stars and different things, but there's this really abnormal just blackness in one spot. It's not because there's no stars there, it's because anything around it or any light that gets around it gets bent and warped and sucked in. Okay, now remember, you might think, well, wait a minute, light's not made of matter. Light doesn't have any mass to it. How can gravity affect it? We never said that gravity can't affect things that don't have matter in them. In fact, if we go back to our equation, to find out the escape velocity of anything is 2 times big G times the mass of the object that is being orbited around. The mass of the actual satellite does not matter here. So light having no mass doesn't have bearing on this. So we can still use it to calculate this. The speed of light is 3 times 10 to the 8th meters per second. We can say that if that was our escape velocity, because that's the fastest things can move, and we know 2, we know big G, okay? We need to know mass and radius to be able to solve this, all right? So if we take a look at our sun has a mass of 1.99 times 10 to the 30th kilograms, okay? So how big would our sun become if it collapsed into a black hole? Basically, what would our radius be for our sun if we did that? All right, so let's solve it, okay? We can set up the escape velocity being the speed of light. We know the mass of the sun. We know G. We can plug these things in. Instead, we're going to solve for the radius now. So we're going to rearrange this to solve for radius. So it's be 2 times gm over velocity squared. We got to square both sides to get the square root out of there. Plug our numbers in, and if we solve that, the radius of the sun would only be about 3,000 meters, okay? So that's not very far across, all right? What's 3,000 meters? It's about 1,700 yards in a mile. So it's not much more than a couple miles radius or a 4-mile diameter of this thing. So really, it'd be really, really small, okay? But our sun doesn't do that, okay? When our sun finally collapses, it won't collapse into a black hole. It'll become a white dwarf and kind of fizzle out over time. It's just not big enough to become a black hole, unfortunately, okay? We won't worry about it because we'll be long gone before that ever happens, but we can calculate it for sure. All right, guys, that is actually everything. That is our unit, okay? So finish up the homework, and we'll get some review going for you guys, and then we'll test you on it. Thank you.